Okay, so very good morning. So in the last class, I have explained about it is a DC load line and the operating point. Okay, and also it is it is graph that is being drawn, that is about VCE versus IC, and if a line is drawn, it is along the points. It is a 0 comma VCC and IC comma. I'm sorry, it is VCC comma 0 and one is it is a 0 comma IC, and if the line is drawn, it is itself is called as the DC load line, and if any of the points existing on on this line is called as the operating point there. Okay, and it is if the operating point is to be placed at the middle of the active region means, so that it is going to give you the exact full waveform, and if the operating point is to be moved, it is toward the saturation means it is going to clip it is some part of the positive part of the signal. In the same way, if the operating point, if it is to be moved, it is near to the cutoff, it is going to it is clip it is some part of the negative part of the signal. Okay, so all that has been studied in the previous class here. And okay, and in this class we are going to see about the voltage divider bias circuit here. Okay, it is concerned to the it is unit 2 of it is BJT and amplifiers. It is concerned to the analog electronic subjects. Is for the diploma ENC. Okay, so in this class I am going to explain about it is what the voltage divider bias circuit, and also it is a DC, it is load line analysis is for the voltage divider bias circuit. It is using the BJT here. Okay, so that if you take the voltage divider bias circuit, okay, so that you can able to see this is an voltage divider bias circuit here. Okay, it is implemented with the BJT, and the actual voltage divider biasing is to be done with the resistors R1 and the R2 here. It is because it is whatever the or it is voltage, the VCC, this plus VCC has been applied, it is to be divided among into the resistors R1 and the R2 here. So for that purpose it is called as an voltage divider circuit. Okay, and if you take the arrangement of the circuit for the it is for this, it is a DC load analysis as an amplifier, it is to be arranged as in this way here. So this is the BJT amplifier, and the R1 and the R2 is acting as of the base resistances arranged under the voltage divider fashion. And what this CC1 is, it is the coupling capacitor, and it is used to take the AC input, and it is to be provided at the base of the transistor here. And the RS is acting as it is the series resistance, it is for the supply here. And RC is it is the collector resistance which is to be collected at the collector terminal, and it is other end of the RC, and the R1 is to be connected with the plus VCC, it is DC supply. And if you take the RE, this is the resistance, it is to be connected at the emitter side, and exactly parallel to this it is connected with the it is one capacitor CE, it is called as it is bypass capacitor, it is used to bypass the AC components here. And if you take the CC2, it is the coupling capacitor at the output terminal, and it is used to couple the output of the one stage as it is to the input of the next stage, or it is used to couple the output obtained at the collector to the load here. And RL is it is the load resistance here. This is itself is an voltage divider bias circuit construction here. Okay, so if you see the DC analysis of this voltage divider bias circuit, so in the DC analysis, all the AC component is to be it is made as the zero. So that if you take the capacitor, it is used to allow only the AC, and it is used to block the DC here. If you take the CC1 capacitor and the CC2, it is acting as an open circuit here. If it is having an open circuit means it is no connection with the AC input here, and it is no connection with the load resistor here. So and in the same way, if you take the bypass capacitor, and it is also acting as the open circuit here. So in the DC analysis, all these AC components, all these capacitors has been opened. And if it has been open means, so what this circuit is going to be visible as in this way here. This is an R1 and R2, it is to be connected at the base. Exactly same here, R1 and R2 is to be connected at the base, and it is connected with the RC and the RE. It is for the collector terminal and the emitter, and it is whatever the remaining portion it is which is interconnected for the CC1 and it is CC2. CC1 part and the CC2 part is going to be disconnected here. So it is what this circuit in the DC analysis it is going to visible as in this way here. Okay, and if you obtain the Thevenin voltage, or if you obtain the voltage at this base, if you obtain the voltage at the base of the transistor VB, okay, this is itself is called as the VTH, which is equal to, this is R2 divided by R1 plus R2 into VCC. This is an R2 divided by R1 plus R2 into the VCC. This is an the voltage divider formula here, or this is also called as, it is using Thevenin's theorem, so it has been obtained as in this way. So this VB is equal to this R2 divided by R1 plus R2 into VCC is the voltage divider formula, and it is the voltage at the base. At this point, the voltage is indicated as the VB. And if you take this R1 and the R2, it is assumed to be in terms of the parallel. Okay, so if it is in terms of the parallel, so as per the parallel arrangement of the transistor, if R1 and R2 is in terms of the parallel means, it is to be given by R1 into R2 divided by R1 plus R2. It is after the simplification of, it is 1 plus R1 plus, it is 1 plus R2. Okay, so in simple, if the circuit is to be simplified for the DC analysis, so the voltage at the base of the transistor is to be given by R2 divided by R1 plus R2 into VCC, and what this RB resistor is to be given as R1 into R2 divided by R1 plus R2, and it is with these values. So what this circuit is to be represented as in this way here. Okay, so this VCC is to be connected for the RC. It is once again the same thing. It is for the collector terminal, and for it is from the emitter terminal RE is connected. From the emitter terminal RE is connected, and other end is connected for the ground. So at this part is going to remain the same here. Only it is simplification also has been done at the R1 and the R2 here. So if this simplification has been, it is replaced with this formula. So the voltage at this point is the VB. So it is to be represented as the voltage VB. And the R1 and the R2 is to be simplified, and it is to be represented as an RB. So it is for this, it is going to be represented as an RB. So RB is, it is assumed to be, it is base resistance, and the VB is the DC voltage applied at the base of the transistor at the DC analysis. So as an R1 and R2 using, it is divide the voltage VCC at the base. The circuit is called as an voltage divider bias. It is based on, it is this circuit. It is based on, it is this formula itself. It is called as an VDB, voltage divider bias. Okay, it is circuit. Okay, and after that, if you want to analyze this for, it is load line here. Okay, I think you know about it is a DC load line. Okay, if you do the simplification for the, it is a DC load line, applying it is Kirchhoff's voltage law, it is to the collector emitter circuit. It is collector emitter circuit means this is the collector emitter circuit. This is the collector part and this is the emitter part. And if you apply, it is KVL here. It is Kirchhoff voltage law, so that you can write the formula as it is with respect to the voltages, so that you can able to see this is equal to the VCC. It is minus the voltage across RC, and it is minus the voltage VCE. It is minus the voltage across RE, which is equal to 0. It is to be connected for the ground here. So the what is this voltage across RC is equal to IC into RC. In the same way, if you take the voltage across RE is equal to IE into RE. Okay, it is so that you can write the formula as it is VCC minus ICRC. It is minus VCE. It is minus IERE is equal to 0. So you can obtain this equation. It is with this circuit. Observe very carefully. Okay, this is the VCC. This is VCC. It is minus ICRC. It is minus ICRC. It is minus VCE. It is minus VCE. It is minus IERE. It is minus IERE is equal to, is connected for the ground, is equal to 0 here. Understood? It is how actually this equation has to be obtained. It's very simple. This is equal to, this is VCC minus ICRC is minus VCE, this minus IERE is equal to 0. And afterwards it is based on, it is this equation, and already you know that the value of the IE is almost equivalent to IC here. Okay, so because IE is equal to IB plus IC is the equation to be considered, and IC is in terms of the milliamps and the IB is in terms of the microamps. So IB is assumed to be the very small if it is to be compared with the IC here. So for that purpose, IE is almost equivalent to IC. So in place of the IE, I am going to substitute here as an IC. And if I substitute here as an IC, it is IC into RC and this is IC into RE. I am going to take IC as the common here. If I take as IC as the common, I can get here the IC as the common, and this is equal to RC plus RE here. And it is whatever the remaining part, it is going to remain the same here. So this is equal to VCC. It is minus IC into RC plus RE is minus VCE is equal to 0. So that you can able to see after simplification, you can get the same equation. VCC minus ICRC, it is minus, it is plus into minus, it is equal to minus here. It is IE into RE, it is minus VCE is equal to 0. Okay, and after that I am going to take this IC at the RHS side here. So for that purpose, IC into, it is RC plus RE is equal to, it is VCC, it is minus VCE. And if I take this RC along, it is with the denominator, I can get this equation as IC is equal to, it is minus of, it is 1 divided by RC plus RE, it is into VCE, is plus the VCC divided by RC plus RE. I think you have understood this. It's very the simple, okay, simplification. Okay, I'm going to take this at the RHS side. Here, this positive, it is to be converted into the negative, which is equal to IC into RC plus RE. And after that, I'm going to take the RC plus RE at the denominator side. So I can get the equation as IC is equal to, it is minus of 1 divided by RC plus RE into VCE is plus, it is VCC divided by RC plus RE. And it is what this equation, it is going to represent the DC load line. So our intention is to obtain what here, it is the DC load line analysis. So this equation is to be compared with the DC load line as it is Y is equal to mx plus c. So as per the it is as per the mathematics, the equation of the line is equal to, it is Y is equal to mx plus c. In this case, what this IC is to be compared with the Y, and it is minus, it is 1 divided by RC plus RE is to be indicated as the M, and what this X is equal to VCE, and this is plus, and what this C, VCC divided by RC plus RE is acting as the constant C. Okay, and if you compare, it is based on this one, what this M, it is called as the slope here. So the slope is equal to, it is minus, it is 1 divided by RC plus RE. And if you take the Y intercept, C is the Y intercept, and this is equal to VCC divided by RC plus RE. I think you have understood. And in this way, it is the slope and the intercept has been obtained here. And after that, it is when IC is equal to 0. In this equation, I am going to place the value of the IC is equal to 0. It is what this transistor is in the cutoff region. So if I place IC is equal to 0, it is going to become as of the 0 is equal to, it is minus 1 divided by RC plus RE into VC plus VCC divided by RC plus RE. So in this case, what happens, if I take this part at the RHS side, so it is RC plus RE and the RC plus RE is going to cancel each other, and I'm going to get VCE is equal to VCC here. Okay, so if I place as IC is equal to 0, I'm going to get here as VCE is equal to VCC. And in the same way, it is when the VCE is equal to 0. In this equation, again, I'm going to place VC is equal to 0. So it is 1 divided by RC plus RE into 0. So if any of the values to be multiplied with the 0 is equal to the 0 itself. So if it is equal to 0 plus VCC divided by RC plus RE is equal to, it is VCC divided by RC plus RE only. So it is in the saturation region, which is indicated as IC sat. IC is the collector current, SAT is the saturation, and is to be given by IC is equal to, it is equal to 0 here. So which is IC sat is equal to VCC divided by RC plus RE. This is the point at which IC is equal to 0, and it is the point at which the VCE is equal to 0 here. And it is based on this one, I can obtain, it is 2 points here. It is thus the two endpoints are VCC comma 0. VCC comma 0 means, so this is the point. IC is equal to, okay, it is equal to 0 is there. VCE is equal to VCC is there. If I take the point for VCC comma IC, VCC comma IC, VCC is equal to VCE is equal to VCC is there, and IC is equal to, okay, 0 is there. So I can write the point as VCC comma 0. VCC comma 0 is the one point. In the same way, if I take the one more point, it is VCE comma IC. VCE is equal to, okay, 0 is there. IC is equal to VCC divided by RC plus RE is there. So I can get the one more point is equal to, it is equal to 0 comma VCC divided by RC plus RE. This is itself is the point. VC, it is equal to 0 comma VCC divided by RC plus RE. 0 comma VCC divided by RC plus RE. It is by joining these two endpoints, a DC load line is drawn here. From the values of the current, we can establish the actual Q point here. Okay, from the actual Q point, so it has been obtained. So that if you want to represent this VCC comma 0, this is the point here. IC is equal to 0 is there. IC is equal to 0 means this is the point on the x-axis here. IC is equal to 0. I am going to take the 0. VCE line here. This is the VCE versus IC. IC is equal to 0. I am going to consider on the x-axis. And what is VCE is equal to, what this is, VCC is there. So this is equal to VCC point. In the same way, from this IC point, this is equal to, the x value is equal to 0 here, and what is y value is equal to VCC divided by RC plus RE. VCC divided by RC plus RE is the y value. And this is one point and this is another point. If I draw the line between these 2 points, this is itself is acting as a the DC load line. And it is for any value of the IB. This is for the base current. What this Q is an operating point. I have explained in the previous class about it is what is Q point here. And if I take the Q point exactly middle of the line here, and if I take these points exactly middle, and if it is to be representing the it is values on the x-axis and the y-axis, you can observe this is exactly equal to half of the VCC here. And in the same way, if I take the ICQ, it is exactly equal to half of the IC. It is equal to half of the VCC divided by RC plus RE. So for that purpose, you can obtain the operating point. It is clear from the saturation current from the circuit is it is the VCEQ is equal to VCC divided by 2. VCEQ is exactly half of the VCC, half of this distance. So this is equal to VCC divided by 2. In the same way, ICQ is equal to half here, VCC divided by 2 into RC plus RE. So it is with these 2 points, the operating point, it is Q, has been obtained as VCQ comma ICQ is equal to VCC divided by 2 comma VCC divided by 2 plus 2 into RC plus RE. Okay, understood? So in this way, the equation has been derived for, it is DC load line here, and for an operating point here. Okay, I am going to repeat in brief the entire concept. It is the voltage divider circuit is to be arranged as in this way. This is collector resistance, this is emitter resistance R1 and R2 is acting as an voltage divider circuit, and what this coupling capacitor is used to connect the AC signal, and what this coupling capacitor is to connect, it is for the next stage or for the output here. And if you do for the DC analysis, all these capacitors is acting as an open circuit. And if this is to be okay, open circuited means it's no connection with the input, and it is no connection with the output, and it is no connection with the ground here, so that you can able to get the circuit as in this way. And after simplification, what is VB is equal to this R2 divided by R1 plus R2 into VCC. Okay, this is an voltage divider formula. And what this R1 and R2 is assumed to be the parallel, so that you can obtain the RB. So this value of the RB is equal to R1 into R2 divided by R1 plus R2, and it is what this VB is equal to R2 divided by R1 plus R2 into VCC. And what this circuit is to be simplified as in this way. And after simplification, so in order to do the DC analysis, if you apply the loop, it is Kirchhoff voltage law at the collector emitter side. Okay, it is at the collector emitter side. This is equal to VCC, it is minus ICRC, it is minus VCE, it is minus IERE is equal to 0. Okay, in this way. And if you assume as IE is almost equivalent to IC, in this IE is to be replaced by IC. And after that, in these two, I'm going to take outside the IC as the common, and the equation becomes as the VCC minus IC into RC plus RE, it is minus VCE is equal to 0. And after simplification of this one for the IC, I can get as IC is equal to, it is minus of 1 divided by RC plus RE into VCE plus VCC divided by RC plus RE. So I'm going to take this component at the RH side, and I'm going to take this component at the denominator side, so that I can be able to get the equation as in this way. And I can compare this equation with the equation of the load line, equation of the line as per the mathematics. It is equal to y is equal to mx plus c. In this case, what is m? It is it is the slope here, which is equal to, it is minus 1 divided by it is 1 plus, I'm sorry, it is equal to minus 1 divided by RC plus RE. And if you take for this C, this is equal to this VCC divided by RC plus RE, which is equal to C. And in this equation, it is when IC is equal to 0. So what is transistor is in the cutoff region here. So this VCE is equal to VCC. If I place as IC is equal to 0, and if I take this component at the RH side, and in this case, what is VCE is equal to VCC here. So RC plus RE and RC plus RE is going to cancel each other. In the same way, if I take VC is equal to 0, I can get the saturation current. If I place as VC is equal to 0, is to be multiplied with the, it is 1 divided by RC plus RE means it's equal to 0. I can get value of the IC is equal to, this is VCC divided by RC plus RE. So I can get the point as VCC comma 0 as the 1 point, VCC comma 0 as the 1 point. Okay, and another point as well, it is equal to 0 comma VCC divided by RC plus RC is equal to 0 comma VCC divided by RC plus RE. And if these points is to be represented in the, it is graph of the VCE versus IC, this is the point which is going to represent the VCC comma 0, and it is the point which is going to represent it is equal to 0 comma VCC divided by RC plus RE. And if I draw the line in between these 2 points, this is itself is acting as of the DC load line. And if I take an exactly, it is middle point with respect to, it is some the base current. Okay, and if I obtain the values of, it is for, it is this point, what this VCEQ is exactly half of the VCC. So for that purpose, VCEQ is equal to VCC divided by 2. In the same way, what this ICQ is exactly half of it is this IC value. So this ICQ is equal to VCC divided by 2 into RC plus RE. So if I obtain, it is point Q, it is equal to VCEQ comma ICQ is equal to VCC divided by 2 comma VCC divided by 2 into RC plus RE. So this is indicating it is Q point for an voltage divider bias circuit. Understood? Okay. And in this case, if you take it is possible question, he may ask you to, it is draw the voltage divider bias circuit, and he is asking you to give the DC load analysis, so that you should do the analysis using it is Kirchhoff voltage law. Okay, so in the next class we are going to study about the features of the amplifiers. Okay, thank you. Okay, thank you very much.